Hello everyone, my name is Hao Xiang, and this is my internship for GFlowVLM, enhancing multi-step reasoning in vision language model with generative flow networks. So let's first see a motivating experiment. So suppose we have an input image containing three numbers, and the model needs to predict the next number in this sequence. So we didn't talk so there are two possible rules. The first one is a arithmetic sequence, like increasing sequence, and then the other one is a Fibonacci sequence. So for a arithmetic sequence, the model needs to predict four because one, two, three, four, right? And if we follow the Fibonacci rule, model needs to predict five. Yeah. So this text has some like diversity of solutions because there are two possible solutions for every text. So this is only a motivating and a toy experiment. So we compare with space model of lava and SFT and PPO and our method called GFlowVLM. So we can see the success rate and the diversity, which is the number of solutions, are both very high compared to the baseline. So this introduced the problem of the baseline, like the SFT and PPO. So here's our motivation. So for SFT, it's lacks of environment interaction, and also it's a maximum or likelihood algorithm. So it's lack of diversity of solutions. And for the reward maximization RL, like PPO, it's always prioritize short-term reward and oversee the long-term dependencies because when we formulate the MDP in RL, we often focus on the transition updates, yeah, rather than the trajectory level update. Okay, and here's our methodology. So here's our inputs, OT and PT. So OT is an image, and the PT is a text prompt at 10 step T. So the prompt contains the a goal description and a history state and actions, and also the action space we can take on the next step. And also the desired outputs, like the model needs to first output the chain of thought first and then take an action. Okay, so on the left is a text prompt template. And also we pass those into the VLM, and then the model needs to first have a CT, which is the chain of thought, and then an AT, which is an action. And then we send AT to an environment, and the environment will give us the next state, ST, AT, and RT. So RT is a reward. And then we store that into a replay buffer. And also the environment will also give us the next action space, big A T plus one. And then we feed it into the next round or next step of the loop. And then after the whole trajectory is done, so we store all the transitions into a replay buffer. And here we store more than one trajectories. So for example, if we store three trajectories and then we update the parameter of the model based on all the three stored trajectories rather than the transition update like PPO. Yeah. And okay. And our loss function, we use different three loss functions of the GFlowNet. Some are from prior work and some we adapt them into our case. So the first one is a variance trajectory balance loss, and the second one is a detail balance loss, and last one is sub trajectory balance loss. And I will talk one by one. So the first one is the variance trajectory balance loss function. So the key idea of GFlowNet is to sample proportional to the reward, so that we can have so the good examples kind of in theory have similar probability to sample from, so that we can the distribution is not kind of stuck on a single mode, so it will kind of model a multimode distribution with different correct examples. And here's the notation here. So X is a terminal state. Terminal state means the terminal as a state of a trajectory. And then S is a non-terminal terminal state. And the Z is the total flow at the initial state. So we can think of flow just like the water flow, and the initial state has the total flow of all the trajectory on the graph. And then the PF is the probability of the forward policy, and PB is the probability of the backward policy. And Rx is the reward X terminal state X. So we only have reward at terminal X rather than non-terminal states. Okay. And then the trajectory balance loss is like this. So we first have the equation one. So that is for a given trajectory from S0 to Sn, so the PF along the trajectory um, times the initial flow at the beginning should equal to the backward flow, like the back, and the last flow is the Rx. And then we calculate, or we multiple all the PB, uh, which is the backward policy. So these two should be equal. And then if you do some like manipulation or like e equation process, then we got this equation 3 and 2. Okay, so this is the variance trajectory balance loss. Okay, and then the trajectory balance loss is simpler. So we suppose we have a sub trajectories from S0 to Sm. So M is some non-terminal state along this trajectory. And then we have equation 4 because the flow at the initial state along the trajectory times the PF, like the forward should be equal to the flow, like we call it backward. Yeah, so that is the equation. And if we take a log and do some equation manipulation, and we got equation 5. Yeah. And here is the detailed balance loss function. So here we only consider a transition rather than a trajectory level. So the same as before. So the previous state times PF should be the flow from the next state times the PB. Yeah, and also if you do some manipulation and we take the log, and it should be the equation like this. And we need to emphasize, so the T here is the terminal symbol that we define. So the detail we recommend to take a look at our paper. Okay, so here are some like experiments of text. We experiment on 3 different texts. The first one is called NumberLine. So this tag is easy to understand. So given the initial image, so the image contain a target and the current number, and the model needs to take two like select action from 2 different actions, the plus or minus, and to reach the target. Yeah, and every time that we take an action, we only minus or plus 1. Yeah. And the next one is called the BlackJack. So this is a stochastic take environment, because every time we don't know what kind of car we will get, and we will see. Yeah, so we only take the action of hit and stand. So this is a simplified BlackJack. And the last one is an embodied AI task called ALFWorld. So we have a task, for example, to put a cool mark on carbonate, and the input is an image that the model can see on the current state. And then we take an action from action space, and the environment will give us an next state. So until we reach the goal. Okay. So for the first tag, number line, uh, the environment reward is one when target is equal to current. So that means we reach the goal. And if we didn't reach the goal, the reward is -1. Yeah, and the length of the trajectory, we set a maximum length, which is equal to 10. Okay. So here's our text prompt. So we have the current number, X, and the target number, something like that. And we need to first do a chain of thoughts, and then we do an action, plus or minus. Okay, so next one is the BlackJack. So also we have an input image, and we can take an action hit or stand. And the environment reward is 1, 0, -1 upon win, draw, and loss. And if we do BlackJack win, so the reward is much higher, which is 1.5. And the length of this trajectory is below 5. Yeah. Okay, and we did some like reward shaping on these two tags, because GFlowNet doesn't allow negative reward. So we made some modification. So our reward is like this reward function, and we have a scaling constant, which is 100 in our case. And also for BlackJack, we just do a max here. So to make sure our reward is always positive or non-negative. Yeah. And here's the last task called ALFWorld embodied planning. So here's an example. So so we have a description of current state, like what we can see around us, and a task description, for example, to put some ways in safe. And we take some action, for example, go to shelf 6 and take waste 2 from shelf 6, and until we reach the target or reach the goal. Yeah. And here's our result on the card games. So we compare with RL for VLM. So there's a PPO paper on the same data set with the same model. So we use Lava as our base model. So we can see from the NumberLine, we perform better than them. And also the OOD is the NumberLine OOD that we just changed the range of the card. So the in distribution is from 0 to 5, and OOD is 5 to 10. So that's OOD case. And for BlackJack, we also achieve better performance than the PPO. Yeah. And we also do some ablation, like we use our policy data on the first section of the table. And if we don't use our policy data, we if we use our policy data, we can achieve even better performance, because our algorithm support our policy data or training. And if we don't use the SFT initialization for the sub-TB and DB loss, then the performance drop a lot. So that means our SFT initialization for the sub-TB and DB loss is very important. Okay. Okay, the last one is the ALFWorld. So here we didn't do the TB loss. Oh, we didn't do the DB loss because we don't have the dense reward for every transition in from the environment. So we just do the sub TB and various TB loss. So we can see our performance on average is better than all the baselines, and also the OD and the diversity. Diversity here is we sample 16 times, and we calculate the number of different trajectory we can find to reach a goal. Yeah. Okay, and here's our training curve. So you can see across all three tasks. So our method converge much faster than PPO. Okay, so here a case study. So we compare with PPO. So we can see the PPO kind of stuck on a action or trajectory because it's lack of diversity and exploration. And our method because we sample proportional to reward rather than maximum reward, so we have better exploration. So we don't stuck in suboptimal state like PPO. So here's a example. Okay, and some takeaways. So we are the first work to fuse or combine GFlowNet with VLM. So that's enable the model to do some like multi-set decision making. And also our fine-tuning method enable VLM to explore richer reasoning paths and diversity solutions. Yeah, and also generalize more robustly to all the tasks. And the last one is the efficiency. So our experiment have showed that our method have better efficiency from the training curve, and also we can have you utilize the policy data, and we can also achieve higher success rate, and also better diversity compared with the baselines. Okay. Thanks for watching our presentation. Let me know if you have any question, and I'm happy to answer them. Okay. Thank you. Bye.